Okay, let's have a class. Let's have a class, and we will move to the exam 1, slide 2. We'll talk about a microscope and the stain technology. So this is the outline of the class. What we're going to talk about is a microscope. So we have a microscope. Based on the energy resource, the microscope could be differentiated as light microscope. And the light microscope, basically we have 3 different types. The one what we did in the lab is called bright field microscope. We will introduce you dark field microscope real quick. And we're also going to talk about a little bit phase contrast microscope. So this is use light as energy. Then we could be using some other energy resource like UV light, blue light. We call it fluorescence microscope. And we also could use argon laser as an energy resource, which is laser confocal microscope. And the last thing we will talk briefly, which is electron microscope. And the electron microscope, based on the characteristics, we could be differentiated as scanning electron microscope. The acronym is SEM, and transmission electron microscope, because we could see the inside, so we call it TEM. And we will be mentioning about these. So this is basically the outline. Now, first thing first, microorganism is too small to see. So we need using a microscope. Therefore, we come out with the first concept we already mentioned in the lab, which is called resolution power. And we know in the lab, the resolution power could be calculated as lambda divided by 2 multiplied by NA. NA is numerical aperture. And we talk about this, we say this is like a size of the engine, like a size of the microscope engine, and the lambda is always 625 nanometer, and this number is 1.25 if we use 100x with oil immersion. So when you see this formula, we will understand what is the resolution power. This is the capability to separate by eyes of 2 closely attached particles, which means how clear you can see it. And certainly we mentioned in the lab this resolution power value should be the smaller the better. The smaller value, which indicate the greater resolution power capability. So this is what we already talked about in the lab section. And you can see right here, the wavelength of the light is a major factor, because we mentioned lambda 625 nanometer is a bright field microscope. What we did in the lab, we all the way turned on to the largest part, to the end. So that's the formula what talks about. And you can see the difference here, which is a resolution in light and the electron microscope. The small image is a light microscope, And the large one is the electron microscope. You can clearly see the electron microscope is much clearer and much focused and less fuzzy compared to the light microscope. So as usual, we already talked about the bright field microscope, all these terminology, and we're not going to be repeated here. So I just wrote here, all these concepts we have been mentioned in the lab, just like a review for you, what is called total magnification. That is the ocular lens magnification multiplied by the objective lens. And we talk about the parfocal, which means once the lens focused, it stays focused, only need a minimal adjustment. And we also talk about a very important method we have to do is oil immersion. Why it is so important, and here the slide tells you, because there is a light refraction when the light passing through different medium, and oil immersion, because the refraction index of oil equals refraction index of glass equals 1.5, which is larger than the refraction index of air, which is 1.0. Therefore, the oil immersion certainly is to remove the air gap. So that's, we already been practicing the lab for twice how to use oil immersion. So all these things we already talked about in the lab, we already practiced, we'll practice again in the next 3 lab sections. So in here, we just skip it, and these slides you could use for the review. We mainly going to spend in time talk about other microscope. So the first one we want to introduce you here is dark field microscope. So what is that? Dark field microscope. Dark field microscope. First thing first, a difference between light field microscope, the background is dark. And the specimen you showed up is bright. Well, specimen, which means the sample, is bright. That's the first thing. Second, why it can be looks like that? Because it's a structure a little bit different. So here is a microscope objective lens. Okay, we draw it briefly. And then we have a stage. Here is the stage. And then we have light resources right here. And we have a condenser somewhere right here. It's a condenser. So what happened is the space between the condenser and the light resource, they put a solid block there. So once they put a solid block there, what's going to happen? The light going through the condenser, going to the stage, and then go to the objective lens, it looks like this. It is perpendicular, which means this angle is 90 degrees. That's the reason which is showing you the background is dark and the specimen is bright, because of this solid block there. So then the third question will be, why dark field microscope is so important? Why we use it? Because there is one group of a very special bacteria, and very important in the clinical area, we call it spiral sheet. Spiral sheet is asexual filaments moved by endoflagella. It is a very special Bacteria, you cannot use a basic dye to do the staining. So we use dark field microscope to do the observation. So what are the examples for spiral sheets? And there is basically a three typical example. Number one, Treponema pallidum. This guy, you heard about it, will cause number one sexual transmitted disease in the world that used to be called syphilis. In the older time, this is number one sexual transmitted disease in the world. What it looks like, we have slides for that. Treponema pallidum looks like that. Can you see how clear it is underneath dark field microscope? Asexual filaments, beautiful asexual filaments, and a little bit spiral, but not really. And the background is dark. That shows the shiny white color there. That's the first one. The second one, Burgdorferi. What is this pathogen for? You heard about this Lyme disease. What is Lyme disease? Lyme disease is in the arm. You have this target-shaped rash. It's coming from a small town called Lyme County in Connecticut in 1970. There's a scientist named Burgdorferi from Montana State University. He's the first person to find it and named it. It is Burgdorferi. It's a spiral sheet. Last thing is on your slides at the end of this lecture is leptospiral interrogans. This is will cause a yellow eye. We call it jaundice. It's kind of indication somehow liver disease. It's usually coming from the rodents and their fecal sample contaminated with a flooding area back in 1970 in the Southwest Asia had a big outbreaks there. That's the reason we need to use dark field microscope, because identify with those typical spiral sheets, Treponema pallidum, Burgdorferi, and leptospiral interrogans, it is important. Now we mentioned about these two are very good characteristics. How about leptospiral interrogans? What it looks like? It looks like this. Looks like this. Hook shape. A very typical hook shape. So showing you a very good color. Okay? And we have a slides for that, which is you have to watch at the end. Leptospiral interrogans, a spiral sheet, hook shape. Look at that. Like a hook to catch the fish in the marine ocean area. That's leptospiral interrogans, spiral sheets. Okay, and this is also underneath dark field microscope. So the color showing up, background dark, the sample is bright. So this is a dark field microscope. Why it is important? That's a reason. Okay, so we're gonna move this out. Now we want to talk about phase contrast microscope. So the third thing we want to mention is phase contrast microscope. It's dark field microscope, so we talk about phase contrast microscope. Phase contrast microscope. A little bit of physics behind this guy. But it's easy to understand, it's not difficult. So what happened is, let's say we have a bacteria here. Okay, that's a bacteria, right here. Okay, the light is coming. The light come, usually it have something like a wavelength. So we use wavelength as an example. Okay, now become like this. So here is like a objective length, for example. Now, generally speaking, the light coming through here is similar. Okay, we do it like the same. Like that, for example. Now what happened is here you're going to put a ring. This is called annual ring. Now the magic thing for this phase contrast microscope is somehow in the middle of the microscope, above the condenser, above the stage, they put a phase ring there. So I use this as an example. It is called a phase ring. Now what's the function of this phase ring? This phase ring will change the speed of the wavelength. So what happened? When you have this phase ring, it's shifted. The wavelength somehow is not like this. It will be, looks like this red one. So it shifted. Okay, it goes through like this, goes through like this. Somehow in here, the peak and the bottom is overlap. And once it's overlapped, what's going to happen? This guy goes here, and they cancel each other. Now, how they do it? This phase ring change the wavelength out of phase. How many is they out of the phase? They either 1/4 wavelength ahead of time, forward or backward. So said very simple. Originally, you're not going to see anything. When they're going through the condenser, going through the objective lens, you see some light there, some reflection. But when I put a phase ring there, the wavelength, the speed going to change, and the morphology going to change. It is around 1/4 wavelength forward or backward. So it looks like this red one instead of this white one. Then, at a later stage, somehow, the bottom of this wavelength and the peak of that white one, they will overlap. If they overlap, they will cancel each other. When you show up here, it is a dark color. So, that means the deviated light with undeviated light cancel each other, then becomes dark. And then there is a large amount of the undeviated light. They actually, which is showing you bright. Now, how dark it is, it depends on the density of the sample. Density of sample, which is possibly means how thick it is, the thickness. So, what's the good advantage of this microscope? You can see some of a live bacterial cell internal structure. That is important, especially some eukaryotes let's say Saccharomyces cerevisiae. You see the internal structure. And this slide shows very clearly, you can see. Light microscope, bright field, you can see a little bit. The far right side is a dark field microscope. You can see a big shining there, is that right? How about the middle one? Phase contrast microscope. Compared to these different microscopes, do you like the middle one better? Yes, because you see the internal structures very well. And when you see these dots there, those dots, it's called inclusion. And those inclusion usually is storage of phosphate or some of the chemicals. And you can see it clearly. Now, I want to point it out that nobody using phase contrasted microscope too often these days. The reason is we already have the electron microscope. We could see much clearer the internal structure. But before the electron microscope comes out, back in 15, 20, 30 years ago, lots of the university have phase contrasted microscope because we can see the internal structure of some live cells without doing staining technology. You can directly to see it. That's the reason. Okay, so it's a magic stuff for the phase contrasted microscope. Now, phase contrasted microscope, because the sample is dark, so some of people also call phase contrasted microscope is dark phase contrasted microscope. So that's a story. Okay, fluorescence microscope. Fluorescence microscope, I want to be introduced you briefly because this is something, a transition stage of the laser confocal microscope. It's a similar pattern, but different energy resource. Fluorescence microscope. So first of all, fluorescence microscope is different from light field microscope. What we already talked about, bright field, dark field, and the phase contrast microscope. They use light as energy. Fluorescence microscope using UV light, blue light as an energy resource. This is the first thing. Second thing, the structure looks like a little bit complicated. You have a short wavelength, you have a large wavelength. When they're going through this blocker, which we call it a mirror, some will be reflected, some will be passing through. But what the good thing for this microscope? You have to do a special stain. The special stain is staining DNA. We call it a fluorochol stain. There is a lot of the commercial products there. The most widely used is the second on your slides called Davis stain. Now, why it is important to stain the DNA? Because it could differentiate dead versus live cell. This is a big advantage. The dead cell, usually it is red color. And the live cell, it is blue, sometimes green color. So green to blue color. That's a good thing, because it's staining the DNA. And this is what it looks like. Look at the shining blue, green color there. That means it's a live cell. And how about the dead cell? It's a red color. It's dead. Now some people will say, how about the purple color? The purple color may be the injured cell. It's a good thing. If you have like purple color, that means it could be an injured cell. So that's a good thing for fluorescence microscope. Because the fluorescence microscope uses UV light and blue light as energy, so it's more focused. But people want to do it more focusing. They come out with laser confocal microscope. Okay, laser confocal microscope. They come out with this guy. Laser confocal microscope, number one, you're going to use laser instead of using other energy resource. Most of the time, what they use commercially is called argon laser. They come from a company called Zeiss. Zeiss. Now, where it is? A big image company, courtesy of Zeiss micro imaging. Look at that, ZEISS. That's a big company to generate all these equipment at, yes?
The blue color is like not visible at all.
Okay, I'll change it. Because I'm doing the gram stain. So I'm going to use using the blue one, but I'll change it. Sorry.
Can you tell us what that says? Like, we can't read it at all.
The argon laser, Zeiss. How about use this?
Thank you.
Argon laser. ZEISS. Okay, now I use blue color. So will we just use this color to, instead of using green, blue when we talk about the gram stain? Okay, that's why I bring it. Maybe I try purple color. We'll see. Maybe not working. So that's why I bring different color, because when I talk about gram stain, it's more good we're using different color. Okay, but thank you for printing out there. That's a Zeiss company. The company is a micro imaging company generated this laser confocal microscope. Now, what's the advantage for that? Same thing. You can use Davy stain to staining DNA of a microbiology cell. And the red one represents dead cell, and the green-blue one represents live cell. Purple one is injured cell. But you have to set up the wavelength of the image. Red cell usually 550 nanometer. The green one 625 to 650 nanometer. The wavelengths representing each of the color. And the good thing, laser confocal microscope is connected to the computer. So you can see 3D images. This is not many traditional microscope you could use except the electron microscope. You can see the 3D images. Why? Because we can see a different layer. That's a very good thing we need to do for bacterial biofilms. So what is bacterial biofilms? Bacterial biofilm is a very special grouping bacteria. It's a matrix. They're stacking together. Most of the time what happened is on the bench or on the food processing plant surfaces. So let's say you're processing beef products. You know the beef, you normally have some generic E. coli. So you clean it, but you didn't sanitize very well. So some of the layer is left on the surface. Once the layer left on the surface, the humidity is accumulated. There are some of the residue food soil there. Then become what? A bacterial layer going to generate. It could be heavy and heavy like this. This is the one we call it biofilm. Okay, you may not can see it, so I'm going to use the other color. That's a biofilm. Now we want to see the biofilm analysis. We want to see the widthness, the length, and also how high it is. That we need to use 3D images, so that's why we need to use the laser confocal microscope. So that's the reason. I did this a long time ago when I was working in Maryland in the USDA, Agricultural Research Service, as a research microbiologist almost 12 years ago, before I came to WVU. This is kind of the research what I did myself. It's about the biofilm. to see the chlorine solution, how they kill the bacterial cell. So you can see the first image. It is most of these are green color. It is live. Then you see the color spectrum there, which is x-axis and the y-axis. X-axis indications the green color. It's all live. And the second thing what I did is I treated them with distilled water. So not many cells died. Some green cells still dominant, and red cell shows up. The color spectrometer kind of seeing some of the extended a little bit, which means a mix of the green and the red color. Then I try to do is I'm going to using chlorine solution. I used 200 parts per million chlorine. Do the treatment, then you see lots of the green cells start to come out, and you see the line right here, the zone 2, which is indicate the red color there, the color spectrometer showing up. That means a lot of the cells are there. There's still some live cell of the green color. The last one is I'm using the surfactants. The surfactants, which is enlarge the exposed area of chlorine with bacteria. What you see it? You see it's very clear. It is right in the middle. It's a big chunk of a light purple color, which means most of the cell with chlorine, with surfactants, it starts to injure. So this is something tells you using laser confocal microscope could be very well to explain the morphology of a biofilm on the surface treated with the sanitizers. But why we have to do these tests? The reason is these biofilms is usually 300 or 500 times resistant for the sanitizer compared to the normal bacterial cell. So the cell which you grow in the broth, we call it a vegetative cell, is usually very sensitive to the sanitizer. But the biofilm left on the surface, they stack together, become a layer, it's resistant to those sanitizers. So we have to do the analyze. And we also have to use surfactants to see whether it helps for the traditional sanitizer. So this is just to show you an example for the laser confocal microscope. Okay? Okay, very quick, we're going to move on to the staining technology. So we finished introduce all of these. And we're going to spend in time talk about staining technology. We will spending a big chunk of time talk about the gram stain before you practice in the lab next week. First section, simple stain. I will skip this part, okay? So because we already talked about in the lab, briefly you make a smear, air dry heat fixing, then you add dye, dry, do the observation. The first lab you already did, and the second, third, fourth lab will be practiced today. And we just barely mention here, tell you the simple stain, the story behind it. Simple stain is because the bacteria is negatively charged. If they grow 35 degrees Celsius, 24 hours. And you have lots of dye. So lots of dye there, which is like crystal, violet, saffroning, and let's say malachite green. Those are positively charged. So they could stack together and showing up the color. And the important thing for the simple stain, we want to see the cell shape, which means the morphology, and we also want to see the cell arrangement. That's the purpose for the simple stain. Now I also want to mention in these slides, we also could do is another different stain. Instead of you use crystal violet, saffron, malachite green, we could do other stain, like nigrosin Indian ink, these are negatively charged. So if they are negatively charged, we call it is negative stain. Let's say nigrosin Indian ink, all those. This is also negatively charged. So once you do that, you're staining the background, and then the specimen showing up. It also reached the purpose. You see the morphology of the bacteria. And I gave you the example is right here. This is negative stain. Streptococcus pneumoniae, diprococcal. You see the heavy capsule there, and the background is dark. This is a negative stain, because we stand in the background and the specimen showed up. Okay, we can do that, but not doing this quite often. Okay, so we want to spending a big chunk of time talk about the gram stain. This is a big deal in the classroom, and we want to explain to you very well before you move to the lab. So I'm going to move also these down and talk about it. You pretty much heard about that before, but here we want to explain to you in the very much detail. Since the blue color and the purple color didn't show very well, so I will use just red color and also yellow color for it. So gram stain. First of all, gram stain is a differentiated stain. And this is a staining technology developed by Hans Gram, a Danish scientist, in 1884. It is a very smart staining technology because they could differentiate microorganism, basically is bacteria, into two groups, which is gram positive and gram negative. What is the color of gram positive? It is purple. Anyway, you cannot see it. It's purple or blue. So blue to purple color. Most likely in the lab you will see it purple, but some people say it's blue. That's fine. And gram negative, it is pink, or some people say it is red. And this is for bacteria. How about fungi? If it's for fungi, we all say it is gram stain blue. Simple, and not positive or negative. Okay, so this is the first thing. Gram stain differentiates the whole microorganism, basically bacteria, into gram positive and gram negative. Gram positive, blue, purple color, gram negative, pink, and red color. Now, what are the major steps of the gram stain? Of course, we have to do the air dry, heat fixing, all those traditional procedures, same as a simple stain. But there is a 4 major steps for a gram stain. The major steps including, number 1, crystal violet. The function of the crystal violet is a basic dye. So we have to add something there, and the purple color is a very strong color. It can show very clearly. The second step, you're going to add so-called gram iodine. It's just a traditional medical iodine. What's the function of the gram iodine? We call it a mordant. This is to make gram stain crystal violet, stain strong. Okay, after doing these two steps, we move to third step, is called using 95% alcohol. The function of this stain is decoloration. Since it's decoloration, so we imagine nothing could be there. So therefore we have to add up something. Finally, we have to add the saffronin. And we call it a counter stain. So this is a major step. Crystal violet, followed by gram iodine. Decoloration, we use 95% alcohol, and the counter stain with saffronin. And every single step basically is 60 seconds rinse. 60 seconds rinse, except for this 95% alcohol is only 10 seconds. Because otherwise, the 95% alcohol is going to remove everything. And the gram stain, we have to make sure one thing is important. The procedure is important. You have to follow these 4 steps. 1, 2, 3, 4, strictly. But the time is not that important. You can stay 45 seconds, 40 seconds, even 30 seconds. It still give you good results. But the procedure, you cannot mess it up. If you messed up the steps, it will not give you ideal results. Sometimes it will be confusing. So the steps is important, time flexible. Steps, follow, time flexible. Okay, next question. It always will ask you, even you took biology class, why gram stain positive stains blue to purple, and why gram stain negative stains pink to red? Why it is? So we're going to explain that. Okay? So this first question, we just say is major steps. The second question is why? Okay, well, we say the principle behind that. Before we talk about this, we need to explain to you a basic structure of a bacterial cell, and we will mention this in the next Tuesday's class, but here we give you some of the hands up right here. Okay, this is gram-positive bacteria. This is gram-negative bacteria. What does the structure looks like? Let's talk about gram-positive first. Gram-positive bacteria, you have this layer. This layer is called cell membrane system. In the cell membrane system, we have, these are basic structure. What are these? Is phospholipids, is that right? You know these learned in your biology class. If you took this out, we call it phospholipids. 2 heads, hydrophilic, like water, and the bottom one, the tail, hydrophobic, dislike water. And do not forget the double layer of phospholipids is inserted with a big chunk of stuff right here. This is protein. So this is a cell membrane. For the gram-positive bacteria, above the cell membrane, there is a little bit of space right here. Okay? This space, periplasma space, and you have a big chunk of all the way on the top. What is the name of this big chunk of the purple color you cannot see? Peptidoglycan. It is very thick. Peptidoglycan composed by amino acid with modified sugar. We'll talk about this real quick next week. And up on top of the peptidoglycan, you may see something like this. Teichoic acid. That's gram-positive bacteria. What is gram-negative bacteria? Same thing. Okay, we mentioned before, just briefly, double layer of these phospholipids But by the way, this is called the fluid mosaic model. You know that. Okay, we have some space right here, but not obviously. Compared to the gram-positive bacteria, have a very thick peptidoglycan. Gram-negative bacteria is very thin, maybe only like this. It is very thin.